and develop new visions and new projects altogether. I would like also to say to the youngest that we used to run conferences like that in the past. And we also used to have a keynote a speech just after the gala dinner in the morning. Quite normal. Back to science now. It's my very great pleasure and honor to welcome and introduce to you Professor Gisela Lanza from Karlsruhe Institute of Technology. We are lucky today to have a talk by her. Her contribution in the field of PLM and in general in the field of production engineering is very high. But we are also unlucky today that a flight was cancelled yesterday and she is not with us. And I would like to thank very much Gisela Lanza for having turned a presentation to a remote speech. Yeah. Okay. Professor Gisela Lanza studied industrial engineering, and it's very important, this point, because industrial engineering is maybe the best training for working on production engineering. Yeah. Yeah. At the University of Karlsruhe, in 2000, she started working as a research associate at the Institute of Production Science, WPK. Then became a member of the management team of the institute and led as a division of production systems that focuses on global production strategy, production system planning, and quality assurance in research, topics that are very interesting for this conference. Since 2012, Professor Lanza holds the chair of production system. She is an active member of the German Academy of Engineering Sciences, ACATEC, the National Platform Industry 4.0, and the steering committee of the Alliance Industry 4.0 in Baden-Württemberg. And finally, the most important for me is that Professor Lanza is the chairwoman of the scientific committee O about production organization in CIRP, the International Academy for Production Engineering. Professor Lanza, the floor is yours. Thank you.
Thank you very much, Daniel, and thank you for having me with you. And it's really a pity that I can't be with you. I try my best after dinner to have here a speech. I'm honored to speak here in the PLM conference, IFIP, and I think you have wonderful topics, really urgent and really important urgent. And my talk here is about the value of product production co-design. And maybe you can say, what is that about co-design? I would like to explain. And yes, it's a sort of new concurrent simultaneous engineering, but I think we have a really new era of this because we are in the world of digitalization or in the revolution of digitalization. So we have really great potential to now integrate product and production planning. And as you heard already, I'm a purely production guy, and I do that research together with our Albert Albers here in Karlsruhe, who is the chair of product development. So when we talk about engineering, in Europe we have more than 17 million engineers. That sounds quite good, but when we look into the country Germany, and we are really an engineer country, then we have to say we are on a declining area. So we have less engineers year by year, especially in mechanical engineer, we have really a dropout. And that's crazy because we need that guys and we need this engineering. And when we look in what engineers, what do they do, we have to say only 1 of 6 are working in our field. In our field of, let's say, product and production engineering. Why is that so? I think the changing the world. Why? It's hard. I think we really have a complex job, and about this complexity you heard a lot in the last 2 days, and I will also speak about this complexity, but I think we have nowadays good tools to handle this complexity. Even 10 years ago already, we had a survey here in Germany, and we thought what has to be done until 2020. And I mean, if you see that, we are still not finished. Still, we have to improve the effectiveness of product engineering processes. Still, we have to manage this complexity, and the uncertainty is really high. Sorry. I think we have good methods and tools, but still they are not standardized. And I think the greatest potential is really that we integrate product development and production planning. And there I would like to stress this new, let's say, only new buzzword, but a really topic where you are all in, is that product production co-design. What do we understand here? We really think that we need a highly collaborative and parallelized planning, development, realization of the products and associated production system. We know that already, but we have to think not only about the operation of that, and but also the business model, and we have to think about systematic circular use of our products and production systems. And so thinking about not only in one life cycle, we have the strong believing that we can model our products and production systems in the thing that we think products are developed always or often in generations. And also the production systems are evolving according to that product generation. I would like to explain that with the model of Albert Albers. He always explains, okay, a product or many products are developed from a generation N to a generation N+1. So an engine, for example, has parts of the old engine. Even if we talk about nowadays batteries or new technology, it's often a part of an older generation. So good example is our German car industry. You see here Porsches, and they look similar. Yeah, a lot, even the design is here similar, but a lot of the parts have the same function, but are getting better over generation. And when we look here now into the production system, we know we have to plan according to the product features the associated, so to say, production system. And in many cases, we plan the production system in an evolving way that we don't have to put everything out, and a totally greenfield production plan if a new product is coming. Car industry or OEMs are somehow different, but a lot of suppliers, machine tool industry, they use their existing production system and evolve them, change that according to the new production or to the new product requirements. And therefore, I think when we talk about a lot of new products, new features, short life cycles, we need really agile production system, or we call it changeable production system with all change drivers and change enablers. Like you see here at an example of a typical assembly line here, our learning factory, where we nicely can show how to do modularity or mobility, scalable systems. So that's needed to really adapt it very quickly to our now products. So we have to think about the strong independencies about production capabilities and product, and we can model that nicely. But it's even getting complexer because we have to think about further generation, and especially when we think about circular economy and circular production, when we want to rework, remanufacture our product, bring components in a second life into a new product, that's important that we have to handle this complexity and this independency of today production system, but also the feature of the product of the future. And herefore we think it helps a lot having this model in mind that we should think, okay, we know a lot about products even in the future, not everything, clear, we want to have innovation, but we can have a reference system in our product development. We can reuse, therefore, a lot of knowledge, what we have in the past, and we do that in the companies, but they are more or less not explicit. So it's implicit knowledge, and we have to explicite it, put that in a tool, put that in tools, methods, that we can easily and be faster in that time to market. And time to market is a good point. We have to be market oriented. So I didn't spoke a lot about business model, but sure we have to model and design then in parallel. And therefore, I think we can then fulfill the customer requirements, and not only the current, but also the future one. So let's say that's the framework we are talking about. And I would like to give short insights what we are doing in that field. And you are also a lot of your work is done within that field. I think to having or to get to a really strong production co-design, we need as a basic system engineering. And in Germany we have a big, let's say, group of people, they are working so-called advanced system engineering. And that's then also a good basic for model-based approaches, model-based system engineering. And clear, digital twin must also be within our toolbox. So starting with that advanced system engineering, one main issue is that Esperanto. I think we are all in one mind that we say, okay, the single system in engineering, for example, mechanics or electronics, are so complex. We try to have one common model and that doesn't work. But we need to have, let's say, a level about that real detail complexity where people can talk to each other. And that's called Esperanto of technology, or you can call it like that. That could be advanced system engineering. That, for example, electronic, he is deeply in his E-plan modeling and designing, but then he has to share his information to the others, for example, to mechanics or construction people. And so they are going up and down, development on a level, can talk to each other, even not only personally, but in a language, in a model world, and then but also be able to go back to their basic, to their detailed work. And for that, I think this model-based system engineering could be really the game changer. Because yes, at the moment everybody has his own models, his own documents, and we try to share a lot still Excel tools, but when we come to that model-based, which understand each other, which shapes then a common, let's interface, that could help a lot. And here I would like to give insight in a project, in a national project Moses, where we really try to do that on the 3 levels: product development with product features and connection, processes, the translation between product and production, so let's say production processes, and then the assets, the resources, and that's the 3rd level, that's then the production system. And if we can do that, model that in a model-based system engineering way, that we have the attributes, the connection, the interconnection, then we can come up with a really, let's say, strong and fast and really good modeling of product and production. And here you see an example of the modeling of welding process. So the vision is coming up with a new product design and automatically your production system is planned. Let's say starting really here with a new customer variant, that's it from the automotive industry, it's a welded part. You know how much part, or you think you know the volume, but you know the CAD file, maybe it's not finished, but then you can then derive you analyze the product, you find out the similarities to past data, and that's what I mean with explicit knowledge. You have a lot of knowledge, and you can derive then process sequences, assign that to resources, and come up with a virtual production system. So that's the task, only based on product data, but to coming up with that, let's say, workflow, and this workflow we dream of that since many years. What can we do for that? And I think our tools nowadays are stronger than in the past because we can handle a lot of data. And that's what I want to show here with the one-time expenses. Let's say you have to set up reference models with model-based system engineering, and having that, you can then easily do it in a specific project in reality. So for example, analysis of products, you see here on points, I will show similar examples later, where you then learn about your product features, also with machine learning, and say, okay, 80% of this product I know already, I have done it in the past, so I can then, let's say, classify all information about that, and set up a reference system where I can classify a new product coming in. And I not only have to do that for the product, but also for my processes, for my resources, and then I can do mathematical optimization and come up with, let's say, virtual systems, as I said before. So the tool chain in a real project, if a customer order is coming in, could look like that. You have this new customer variant, then it's classified according to the reference system. You derive a process order, a process chain, assign these machines, and come up with that visualization. And that works already, not for everybody, still a lot to do in this model-based system models, in the reference models, but I think it's really worth to set up that. In another project, we came later. Here the product function is fixed, but still as production planner, we try to optimize the process chain. Can we even pursue the product designer to change a little bit their deviation, their shape, to having better processes, to having better production, and therefore cheaper. You know, we production guys, we always have to, let's say, to optimize the cost in the production. And therefore we start with that, let's say, fixed product model and fixed manufacturing technology model, the chain, and try then to find out what is the degree of freedom in changing the product. But this product has to have the same function as before, because let's say that the design phase is already closed. But maybe we can change a radius according to the better technology. Could we change a technology and have a better technology, faster, better, cheaper, and so on? So can we change technology, modify the technology, and even look in the future and say, okay, we did that a lot with generative additive technology, so we know at the moment the capability of this new technology, but we also know that in a few years we have a huge learning phase, learning curve, so we know in 3-5 years we have a higher capability than today. I would like to give here an example. It's turbine blade here from Siemens within that KitKat project, and when we say at the moment, this, let's say, this shaft, the top of the shaft is done by SLM, by selective laser melding, because of this cooling issues in the plate, in the shaft, but in the wood, in the food, that's still casting. I mean, current phase, in many cases, it's totally casted, but yes, the first one are also done partly by additive manufacturing already. And then we try to do optimization, try to find out, can we change can we have some modification in the product? Could we think about new technology? And for example, come up, okay, if we could do everything with even the food with SLM, could we even then reduce the volume? And how much should we reduce the volume that we came up with the same characteristic of the product? Because the material characteristic is here different. Is that possible? Is it not possible? On the other hand, we have new technology like the laser metal deposition, that we can have that's working bigger volume, that we can come up with a faster process. So we could do that, the food with LNG. So we do that iteration and come up with, let's say, modification in terms of cost, in terms of material characteristic, but then in the end, clearly the designer and the responsible product manager have to decide if that is possible, because it's clearly only one part of a bigger product. So we do that iteration, coming up with optimized solution. For example, here the solution could be that we have a conventional part. We can compare that with that starting part, which we have seen, this hybrid, where we have additive in the top and casting in at the food, or compare it totally with additive. So it gives us a good assessment of different technology, changing, so to say, or changing a little bit, finding out what is our field of freedom to change here in the technology, also in the product, without having a totally new product design. So that's a clearly topic where you see we as production guys would like to change something, but we only can do it in a really strong, let's say, not only collaboration, we have to test it, simulate it, verify that if that really works for the product guys. And if we can do something like that, we can come up with that digital twin. And I really think that's a main topic where we all work on it, because a digital twin is much more than only a virtual representative. So we start with that, we have the understanding here of that definition. I mean, there are a lot of definitions, but we think, okay, we have at the basic a digital master. And this digital master, ideally, it's done with model-based system engineering, as I showed before. And if I combine that, or let's say interconnect that with the real data in the real world, in the real time, in very high iterations, then I have digital shadows together, digital master with digital shadows, when I can connect them and then even use algorithm simulations, correlation, then I talk about the digital twin. And I would like to give here also examples. As I said before, the digital master can help a lot to come up in the planning phase. I mean, sometimes people say also the digital master is the digital model. And as we said, we spoke about model. But what can we do? We can come up nowadays a lot with we can handle our data and be much faster in terms of optimize and routinous works. And here in a huge project in Germany, in Ajax, we try to have a design assistant for the CAD designer. So in this company, a lot of similar products, as you here see, this sensor components. We try to process them to come up with a digital representative, find out what are the features of that product, and then try to classify them and help the designer to come up with a similar solution. Because, I mean, that is a simple part in a complex product, and you know, we love to come up always with new solution, but in that time, if I talk about this housing and flanges, maybe it would be really better to think about what do I have already in my CAD, in my product, let's say, spectrum, and can I use a similar product? Maybe I have to change one or two features. Again, this product generation development is very important, but in that case, it's not a generation, it's more a variance, a bright variance, a lot of variance. They have thousands of these flanges in houses. So how do we do that? We try to have really unlabeled CAD data, and that's important. I mean, we have to use that machine learning algorithm, and at the moment we have to put a lot of human work in that project. But I think it works because then it's getting better and better, and in the end the system will learn automatically. So we try to use that CAD models, put them or represent that in point clouds, then use such kind of machine learning algorithm encoder, where we then try to set or to, let's say, represent this CAD model in one vector, in this one latent vector. Why? Because if I can, then can I easily calculate it, and if this vector is similar from one product to another, so for example here in this graph shown, if the distance is not far away, I know these products are similar. And I didn't have to describe the product before with metadata like volume and material and stuff like that. I only have the CAD model, and that is done then automatically. And you can do it with a lot of data because it's really strong in calculating it. Here you see some examples. Adapters, cover, flange, this product. And you see here the housings are not a cluster at all. Why? Because housings can look very, very different. But the algorithm works. If we look here at that flange, here this green one and this housing on the right side, they look really similar. And you see that the algorithm found out that. So yes, in that terms, the algorithm couldn't find the reality, because in the right side it's a housing, on the left side it's a flange, but it works in terms of similarity, and that helps a lot. For example, in other examples, covers, here again, covers and O-rings look similar. So what can we do with that? The designer can come up with a model, and then the system can clearly show him what it is already in the CAD system, what other colleagues have already engineered or designed, and we can do it automatically with that latent vectors. And if you compare that with commercial solution which use for that similarity check meta information, it is the same. But as I mentioned, it's machine learning. It works even better if we have more and more data, and that's what we have to set up at the moment, I think. So what we have done already is, in that kind of research project, we can set up a prototypical implementation that in a commercial system like Creo. And the next part is really that the engineer starting to design something has the first shape, and then like a wizard, the system then tells him what to do next, or what is the final solution. So it's not only a similarity check at the moment, but it's also proposing what is the final solution of this, what he wants to design. So I think here we will see a lot of advantage or a lot of progress in the next year. Combining now such kind of digital models, digital masters, with digital shadows, as I said, with the reality, then we can come up with to digital twin. And here I would like to stress that I'm a production guy, so I would like to combine product with the production system and come up here with a very good solution. And therefore we have not only have the product master, we also have to have the production master, as we have seen in the example before. So in a virtual domain, we blend that, and then in the digital shadow, combine that with the physical domain. And the physical domain, you see, we have to, let's say, connect these sensors, this data. For example, end-of-line testing, we can then connect the quality function according to our model, or the inline sensors. And having this real-time connection, we can come up with a digital twin. In this example, we try really to optimize the process and measure the measurement data from production and have a much better function-oriented quality control at the end of line testing. So one idea what we have to, with that digital twin is really come up with adaptive quality control, to come up here with choosing selective assembly, adaptive manufacturing. But what I would like to stress here, I can even then really adapt my tolerances in the co-design, because I know what kind of function I want, and therefore I can really close the loop, close the circles, and come up with, in the product design already, with a production-oriented, function-based design. So I really think we have a great potential with that kind of data, with the data analytics, with the methods tool we have now. And as I mentioned, model-based system engineering is a great issue. So thank you very much for listening to me, and I would be very happy now to answer your questions.
Thank you very much, Professor Lanza, for this very inspiring presentation. That brings your vision of the production of the future, and I think that we have now lots of inputs for the discussion. Who wants to start?
Well, thank you very much, Professor Lanza, for your very interesting speech. You started your speech by telling us that we are trying to manage complexity, and I fully agree with this statement. And we propose systems in order to solve complexity, which become complex, more and more complex every day. What do you think about that, and what could be the good balance between both?
I'm not clear sure if I understand your question quite good. I think if we have external complexity, we can only manage it with internal complexity. That's a basic knowledge. So I think our models are complex, but they are somehow capsulated. I mean, all the kind of algorithms, sometimes they are not, they are called black box models, because we not exactly know everything in that kind of models. But I think we have to have complex models to solve our complex world.
Yes,
was that your question, or could you maybe...
Yes, that was a part of the question, but by creating complex model, we make the system more and more complex also. So is there a good balance between all this complexity and all the systems were created, or is it, should it be better to try to simplify the system themselves?
You think we can simplify products?
Why not?
I'm totally with you, but if the product is complex, how could we have simple design tools? I think the simplicity should be in applying these tools. And if you have seen these change enablers, I think the same issue is according to models. It should be modular, it should be universal, it should be clear interfaces, it should be scalable, and so on. So I think we should try to have modular, easy to use models, but I don't think that we can, as designers, as production system, make a complex world easy.
Okay, thank you very much.
I have also a question. I was surprised that your title was, I don't remember exactly, but product production co-design, and not product de-production co-design. And you started with a definition where you included the reuse of materials in terms of circular systems and circular economy for both product and production system. Does it give more complexity, or does it simplify some things in the future for modeling the systems?
I think the next 10 years it will be even more complex, especially for production guys, because we have to handle this high variance and this uncertainty in the product. Each product which is coming back from the field is not clear defined anymore, determined. I mean, all these characteristics, I have to inspect that, and if I have huge uncertainty in the features of that product, in the deviation, in all that kind of, let's say, rust damage and stuff like that. So we have unicate products. We talk a lot since 10 years in Industry 4.0 that we will have lot size 1 with cost of a mass production, but this time we have lot size 1, but even this lot size 1 means really individual products, because even I talk a lot about serial production, as you have seen these examples, car, automotive supplier, machine tool. So even if I have, let's say, this parts, these gears, and I produce that in thousands and millions, each part or each product it's coming back has a specific, individual, unique characteristics, and therefore it's getting much complicated. On the other hand, what makes me more confident that it will work is that we can go more into, that was the question before, in easy modular designs, that we can have better de-assembly, better this design for Öko, what was built up in the 18th. Maybe we will really have a revival, and again, a revival means also it's getting better, yeah, and more powerful.
Okay, thank you.
Thank you for the talk. In the context of Industry 4.0, it's always the term disruptiveness pops up. And what you showed is more or less the evolution of products and production processes. Also with the machine learning, you build up on historical data. So I guess you have you showed a lot of industry cooperation. So when you face reality, does Industry 4.0, does it need to be decoupled or considered separately separately from the buzzword disruptiveness?
In my talks to Industry 4.0, I always show two dimensions. You can have disruptiveness, but I think always disruptiveness is coming from the product. If you want to do revenue as a product guy, it could be that your product customer doesn't want your product anymore. For example, combustion engine. Even the combustion engine will live a few years more, and they really have to come up with optimization in the next 20 years because it has to get much less expensive. But yes, your product can be disruptive, but the production guys, we can't be disruptive. We can only use new technology. That's the biggest disruptive I saw in the last 10 years, and I can't imagine what's coming up. I mean, quantum computing, yes, we can then solve problems. I mean, if you talk about that, that's disruptive. I say that's only better tools to solve our complex tasks. So in many cases, we can optimize existing systems, and you are totally through. I think 80% is something what we know, and we combine that with really new features. Again, I'm talking about Industry 4.0 in both dimensions. Here, product, it could be disruptive, but the other dimension is production. And here I want to increase and have to increase effectiveness and efficiency. So Industry 4.0 is everything, and not only the disruption, but also the evolution. So we often say, is it a revolution or evolution? I think we are middle in the evolution, but for many products, it can be really a revolution. So Industry 4.0 is both for me, and doesn't mean that I have to separate it. And still, what I'm talking here is not about totally disruptive. I mean, if you really come up with a totally new product and never seen it before, you can't use that. But we also do a lot of projects with the new mobility, so battery, even fuel cells production. And this fuel cells production, we have companies, they deal with fuel cells since the 90s. Even myself, I worked with Daimler in that topic. So it's not like that we don't have any knowledge about that. But the product cycles are really fast. I mean, that's an uncapable or enabling technology, let's say it in a positive way. So it has to evolve very fast to come up with a high efficiency. And I think especially for new technology, the cycles are getting much faster, and the difference from one product generation to the next is much higher than in a let's say, capable technology.
Thank you. The questions are, I can see. Yes, you said that it's not really disruptive in the production system, it's just increasing. It could be disruptive in product. I think that at the moment we are going more to service than products, meaning that it is a supply chain that could be disruptive. What do you think?
Yes, but we have, I'm doing a lot of research in global production networks, as you maybe know, and we have a high hysteresis between change need and the really change in a production network or in a supply chain. We are not fast in that term, and that's what the problem causes at the moment. So yes, we will see a decoupling, we will see a more regional supply chain, and we call it disruptive, but actually disruptive is that it doesn't work. The solution is, again, evolution.
Okay, thank you. If there is no other urgent question, I think that I can close the session to be on time for the next session. I would like to thank you, Professor Lanza, very much for this very inspiring talk and the discussion that we have.
Thank you
Is it
very
okay?
much. I would like to say thank to my team and thank to your team that we managed that to do it in a virtual way, and I wish you a wonderful conference.
Okay, and you are welcome to Grenoble when you want. Yeah.
Yeah, I will come, that's for sure. Thank you very much.
Okay, bye-bye, Gisela. Je ne sais pas annoncer la suite.
Just before the parallel session, because we will